So we were discussing second order systems from the perspective of stability, and we essentially concluded that if we have a second order, if we have an open loop system whose L of S is of the form A naught, again it's causing problem. I don't know why. Lower half of the screen probably doesn't cause problems, so let me write on the lower half. L of S is A naught by 1 plus S by P1, 1 plus S by P2. So this is, by the way, open loop gain. And assume P1 and P2 are real. Then what did we see? We saw that the closed loop gain, that is V naught over Vi, was of some form, some numerator by S square by 2 zeta omega n s plus omega n squared, right? And how this closed loop system is going to behave was a function of the denominator. And more specifically, it was a function of zeta. And we saw that if zeta is equal to 0, right? If zeta equal to 0, then it's like an oscillator. It's an underdamped system. It keeps on oscillating. If zeta is equal to 1, it's critically damped. It doesn't overshoot. If it's between 0 to 1, it overshoots, undershoots, rings, and settles eventually. So, then we also saw that while coming from L of S to V naught over Vi, we also saw that there was a certain relationship between zeta and P1 and P2. And we further concluded that in order to make the closed loop system critically damped, so this is closed loop. In order to make the closed loop system critically damped, we had to ensure that is zeta equal to 1. For zeta equal to 1, we had to ensure that P2 had to be 4 times omega u loop, where omega u loop corresponds to the loop gain, where the loop gain goes to 1 for the open loop system, right? So it's an interplay between how the closed loop system is going to work, given that we know the transfer function of the open loop system, or more specifically, the loop gain. So again, if I write in terms of if I sketch the roots, so let's say this is the roots of L of S. So let's say this is sigma, this is j omega, right? So we assume P1 and P2 are real. So we saw that, let's say this is P1, this is P2. And we are let's say we try to plot the roots of, so let's say we are plotting the roots of L of S. Here we are plotting the roots of V naught over Vi. So for zeta equal to 1, for zeta equal to 0, let's say for zeta equal to 0, for zeta equal to 0, where do you think the poles will lie for the roots of it, or rather, I shouldn't say roots, I should say poles. So for zeta equal to 0, where do you think the poles of V naught over Vi will lie on this S plane on the right hand side? On the j omega axis. More specifically, I mean, I am trying to find out the root of the denominator. If zeta equal to 0, it will be on plus minus j omega n, right? So the more important part is it will lie flush on the j omega axis. So this is kind of marginally stable, right? If it just goes to the right, it becomes completely unstable. Now, this is for zeta equal to 0. And for if zeta is not equal to 0, let's say zeta equal to 1, where will the roots lie or the poles lie? Pardon? Let's say zeta equal to 1. Look at this equation. Zeta equal to 1. left side and can you get the value? Yeah, exactly at minus omega n, right? Both of them will lie on minus omega n. So somewhere over here, minus omega n. And so omega n is real. So you will have real roots. And if you go below, if you go zeta equal to more than 1, if you go zeta greater than 1, can you predict what will happen? Where will the roots lie? Right. So this side and right side, right? So this side. So, but the key thing here is that it will lie on the real axis. Okay. But now if zeta is less than 1, now if zeta is less than 1, so what will happen? The roots will split. This will do something like that. The reason I'm saying all these things is because you see that the locus of the root, right? The movement of the root as you change zeta is going from being all real to imaginary towards instability. And if it ever crosses this side, you're dead, right? But fortunately, in case of second order systems, it's not a problem. It never crosses up. Zeta equal to 0 is the minimum. It doesn't really go beyond that. So we are good. But we can already see that this can be a potential problem if we have higher order system, because in a first order system, this was never a problem. In a second order system, this is probably marginally a problem. If you have higher order systems, then it is conceivable that the roots can go to the right half plane. The closed loop poles can go to the right half plane, and you might land up into trouble. Okay. So, and we also just to complete the thought, and we also, from whatever we did in the previous class, we also drew a parallel between the location, not the exact location, but kind of what will happen if zeta, what does zeta equal to 0, what does zeta equal to 1 mean for P1 and P2? And we saw that for zeta equal to 1, P1 and P2 has to be far apart. That is a given. But we also saw something important. We saw that if P1 and P2 not only have to be far apart, but P2 also has to be 4 times omega u loop. Or in that case, it was 4 times A0 times P1. Right? So information of the roots of the closed loop system also gives you some actionable information on the open loop system. Why do I say actionable? Because when you design a feedback system, you design based on whatever you see for the loop gain. Right? You plot the loop gain and you find out the pole locations of the loop gain, and you try to hypothesize, if I close the loop, what will the closed loop system look like, right? Or what will be the behavior of the closed loop system? So we seldom do a full analysis of the closed loop system. We always look at the open loop system response and try to figure out what the closed loop system will look like. Hence, you will, when you are doing your analysis, the next assignments and subsequent assignments, you will always limit yourself to analysis of the open loop system. And we will try to hypothesize what's going to happen to the closed loop system looking at the open loop system. Okay, so that is why this relationship is important. Okay, now that we at least that I hope that you are satisfied with whatever the requirements for the open loop system and the closed loop systems are. So now let's see if we can develop a framework for a higher order system. Okay, so again, what are we looking for? We are looking for a higher order system, which means poles of more than 2, right? Poles of more than 2. But the requirement is, in the closed loop system, the poles of the closed loop system should not go to the right half plane. So that's essentially the requirement. Okay. So now one might say that what's so big deal? I can write out the polynomial of the closed loop system and try to figure out the pole locations. That is doable, but that is severely limited because you cannot anything higher than third order you don't have a generic solution of finding out the roots of a polynomial, right? So if there is no generic analytical solutions, forget about developing an intuition. That's not going to happen. So what circuit designers, mathematicians over the years have said that if that is not possible, we'll find out other bypass methods of figuring out whether this is possible or not. And Cauchy and Nyquist came up with, few awesome ways of figuring it out, right? So a quick refresher. Let me just state what they say, and then we'll use those. So let's say we have a let's say we have a transfer function L of S. This has this can be represented as, let's say, 1 by some d of s, where d of s corresponds is basically denominator, but it has multiple roots. Okay, so what Cauchy said was, it started off from being pretty obvious, then it went too profound. So let's say I am plotting this. Let's say this is the S plane. This is sigma, this is j omega. And let's say this is the L plane. This is, I'm plotting real of L and imaginary of L. So what he said was, let's say I know that there is a root of d of s somewhere over here. Let's say we know that. Okay. So if we know that, what can you comment on the corresponding value of d of s? Let's say I call it d plane, not L plane. Let's call it d plane. Okay, so what can you comment on the corresponding value in the d plane? So let me repeat my question. So the question. So even before I repeat my question, let me try to. It is jumping around today. Okay, so let me rephrase. Right, I think I confused you. So let's say I take one point in the S plane, any arbitrary point, and I call it sigma 1 j omega 1. Okay, and I find out what is the corresponding value in the d plane. So I will have a value, right? I'll have a value of d of sigma 1 j omega 1. And that value, I can plot that, I can mark off that point somewhere here. Right? Maybe it maps to this point. Similarly, I can find another point, maybe that maps to this point. So similarly, I can mark off all the points in the S plane to a corresponding point in the D plane. Do you agree? Okay. So if that happens, now among all these points that I am marking off, I will also have this point. Right? So what will that point map to in the D plane? 0, right? So this point will map to 0. Okay, so that is pretty obvious. Now, what Cauchy came up and said that, which is kind of profound, but also slightly intuitive. He said that, so let's say I know that this root exists at wherever I have shown you. And let's say in the vicinity of the root, I find one point and mark its existence on the mark the corresponding value on the D plane. I mark a adjacent point and do that. Maybe it will be here. Maybe it will be here. So I'll do all these things, and I will do it in such a way that I come back to the original point while encircling the root. So what Cauchy said, that if you do this, what will end up happening is you will find another closed contour in the D plane. I don't know how the contour will look like, but what will end up happening is that it will encircle the origin in the D plane. Right? So again, probably intuitive, but if you have to do the mathematical analysis, I would encourage you to go back and look at the derivation. But we'll use this information, right? So if this is true, then you can readily see that this has profound impact for all control system, all stability related problems, right? Because ultimately, what are we looking for? We are looking for the case where we are trying to figure out we are essentially trying to figure out if on the entire right half plane, if a pole exists or not, if a root exists or not on the entire right half plane, right? So let's say this is sigma, this is j omega, and this is d of s. So we are essentially trying to say, the question that we are asking is, we are trying to figure out if there is a pole anywhere on the right half plane. If there is a pole on the right half plane, what's going to happen? I'll find, if I do this contour, if I go around this contour, somehow I'll find a contour which will encircle the origin, right? So if I can do this experiment, and I go around the room, go around this loop, right? And I correspondingly plot the contour on the D plane, and I find that the contour encircles the origin, then I know the system will be unstable because a pole exists, a closed loop pole exists on the right half plane. Okay, so this is very useful because, again, we are not particularly bothered of how unstable it is. We are only bothered about whether it is unstable or not. Right? At this stage, we are only bothered about whether it is unstable or not. So then if we can do this experiment, this is right. So this is, as one of my professors told me once, that let's say if you know that maybe you have lost your key inside the classroom, you know that it probably exists somewhere, you don't know where it is, or you have the ability to sweep the entire contour, right? What you will do, you'll put a rope or something, and then you will drag the rope out and see whether the key comes out. Right? You are not particularly bothered at which corner of the room it exists. Whether it exists or not, this is something we are bothered about. So similarly, you can think of that this root is the key that you are trying to find out, and this contour is the rope that you are drawing across the loop. And the information is whether on the other plane you are encircling the origin or not. Okay. Okay. So now what is the application of this? The application clearly is that we know everything about L of S, but we need to know something about V naught over Vi, which is of the form of L by 1 plus L. Right? Something times L by 1 plus L. Right? So we are essentially trying to say is, given, what we are essentially saying that if I go around this contour, from starting from, let's say, 0 to infinite j omega, go around in this radius of infinity, let's say this is radius of infinity, come back, and we try to find out what we are looking for. We are trying to find out in the 1 plus L plane, because the denominator is 1 plus L now, in the 1 plus L plane, whether I have an encirclement or not of the origin. If I have an encirclement of the origin in the 1 plus L plane, then I know that a closed loop pole exists on the right hand side. Okay. So then Nyquist said that, okay, why do 1 plus L? I can as well do L and try to see whether instead of encircling the origin, whether I am encircling another point which is minus 1. Right? Roots of 1 plus L is equivalent to saying the solution of L equal to minus 1. Right? So what he is then went ahead and said that, so I'll not bother about 1 plus L, because L we already know, right? L we know fairly easily. So my key point of interest is minus 1, 0, right? And I will see if this happens. If this happens, I know I am unstable. If this doesn't happen, then unstable. Okay. Any questions till now? I'm assuming you know this. I'm just running through it. Okay. Fine. So then circuit designers, and with the help of Bode, figured out that we probably don't need to do all these things also, because plotting Nyquist is not a very trivial job, right? But plotting Bode plot is a very trivial job. You can basically have j omega axis and mark off each point. So let's see if we can figure things out using Bode plot. And why is this relevant? This is relevant because, so see what's going to happen. So L of S will be of the order of some number. I mean, it will have some zeros and some poles, right? In general, it will have some zeros and some poles, and we have only dealt with all pole systems till now, but it's not necessary. You can have some zeros and some poles, but almost, not almost, in all practical systems, number of zeros are less than number of poles. Because you can think of it in this way, that L of infinity will always go to 0. Because when you, L of infinity means an infinite frequency. At infinite frequency, you'll have some capacitor somewhere which will short off. Right? Ultimately, you are not going to get an output at infinite frequency, which essentially means that, the backhanded way of saying that number of poles will be more than number of zeros. So why again this is profound? This is profound because, which means if S tends to infinity, right, L of S goes to 0. Which essentially means that I don't have to bother about this part of the contour at all. Because in that half circle, in that semicircle, I know that my L of S will always be in the origin. Right? So most of the contour goes off, right? I don't have to analyze. So what about this part? What about this plot? So see, this part is, I am traveling along the j omega axis, which means I am evaluating the transfer function for all values of omega. No sigma required, only all values of omega. And what is the plot? Well, what is that plot that gives us that information of L of S for all values of omega? That's the Bode plot, right? So essentially what we are saying is, we don't even have to look at the Nyquist. We can simply look at the Bode plot and derive all the necessary information to figure out whether our system is stable or not. Okay, so now, so if I have to do that, so before I move on, the last thing is, what about this part of the plot? This part of from minus j infinity to 0. So this is all real systems. Since these are all real systems, we know that L of plus j omega will be equal to L of minus j omega, right? So again, we essentially don't have to bother about, we don't have to plot the bottom side also. All we have to deal with this part of the contour. And the rest of it, I will either be symmetric or will be 0. So essentially, Bode plot is good enough. Okay. So, but before we move on to Bode plot, we'll at least have to do a parallel analysis of Nyquist and Bode once to figure out whether we are good or not. Okay. So that's what we are going to do next. Okay. So let's take again a first order system. Let's say L of S is A0 by 1 plus S by P1. So what I'll do, I'll plot the Nyquist on the left and Bode on the right and try to get a correlation. So I'm plotting here, this is real L, imaginary L. Okay. So ultimately, I mean, we are looking for whether I will have encirclement of this point, minus 1, 0. Okay. So we have to start from, where are we starting from? We are starting from 0, right? So when S is equal to 0 or omega equal to 0, where should I mark off the point? A0, which means where in this plot? On the x-axis, somewhere far in the right? So this will be somewhere A0. Okay. And now I increase the what am I doing? I am going along the j omega axis, right? I'm going along the j omega axis. So in essence, I am always interested in L of j omega. Even though I'm writing L of S, I am kind of interested in L of j omega, which is N0 by 1 plus j omega by P. So L of j omega has two components. One is magnitude, other is phase. So magnitude of L is N0 by under root 1 plus 1 square, 1 square. And what is the phase? Minus tan inverse omega by P1. Okay. So what is the magnitude part telling us? The magnitude part is telling us is that as I keep on increasing omega, the distance from the origin is reducing, right? So which means I'll go closer, at least I'll go closer to the origin. And what is the phase part telling us? Should I mean, I can, from A0, I can go closer to the origin this way, this way, this way. Downwards, because phase is negative, right? So I'll go downwards. Fine. Now, and this will keep on going, but what are we ultimately again interested in? We are interested in where do we end up when we go to infinite, right? So clearly, when I go to infinite, the magnitude is 0, which means I'll hit the origin, but I'm more interested in at what angle I'm hitting the origin, because ultimately I need to figure out whether I'm close to that -1 point or not. So in this case, at omega equal to infinite, how will I hit the origin? I can hit the origin from this side, from this side, from this side. Yeah, it will never go to the left-hand side because the maximum angle is -90 degree. So in principle, it will actually, if you are very close, so it will be 90 degree, -90 degree and hit. So this is what's going to happen. Okay. And now note that in this part of the semicircle, I'm always stuck at the origin. And for this part of the trip, I will do this because it's symmetric. Okay. So clearly, you're far away from the origin, unconditionally stable. Okay. So what is the Bode plot, Bode equivalent of that? The Bode equivalent of that means I'll have to sketch both the phase and the magnitude. So let's say that I'm sketching the phase, I'm sketching the magnitude. So at DC, a very high gain, I'll hit P1 somewhere, fall off. Here at the angle will be at DC, I'll have 0, P1 minus 45 degree, and then probably go to minus pi by 2. Okay. Okay. So what is this telling us? This is essentially telling us, see, I have never gone to the third quadrant because the maximum angle is minus pi by 2. Since I have never gone to the third quadrant, I don't have to bother about anything else. Okay. So unconditionally stable. So let's do the second order system. So let's do second order, all pole systems. So again, real of L, imaginary of L. Angle of L will be minus tan inverse omega by P1 minus tan inverse omega by P2, and mod of L is monotonically decreasing, so I'm not writing it. It's kind of obvious, right? Okay, so we'll do the same experiment again. So at omega equal to 0, I'll be somewhere here, A0. As omega increases, I will again go down. But now if I see where at omega equal to infinity, I know I will hit the origin, but from which angle? Minus 90, is it? I mean, at omega equal to infinity, this will give you minus pi by 2. This will give you minus pi by 2. I will hit with minus pi, right? So I'll hit here. So clearly I'm going into the third quadrant, which means I have to be careful now, because this is the danger point. Okay, so this will probably go something like this, and its equivalent, the brother will go like something like this. Okay, so now can it ever cross -1, point? Because if it has to go cross the -1, point, it's not, I mean, this plot has to go to the second quadrant, right? It has to do something like this, right? But it cannot ever go because the maximum angle is -pi. Right? So again, so second order systems are always stable, but the issue is that we are getting closer and closer, right? We are getting closer and closer to instability. So now, so we need to have a measure of how close we are to instability, because we saw that in case of zeta equal to 0 or zeta less than 1, you had ringing, which means that it's quite possible the system will take forever to settle if you give it a step input, which probably will not be acceptable in most applications, right? So which means that it's not only sufficient to say now that we are stable or not, right? We need to see whether you have sufficient margins. You have sufficient margins from stability, right? It's like whether I am at the edge of the cliff or I am slightly away, right? So I'll have to be more careful if I am at the edge of the cliff, or at least I need to know how close to the edge of the cliff I am. Okay. So now what is the margin that we are kind of interested in? The margin that we are kind of interested in is the following. So the issue is, the problem is L equal to -1 point, right? This is the problem. Okay. So at L equal to -1, which means I'm interested in the point where mod of L is equal to 1, right? And we are trying to figure out what the angle is, right? If then you are cutting that -10 point, or you are touching that -10 point, then you have a problem. So mod of L equal to 1 is, in a complex plane, is a circle, right? Mod of L equal to 1 in a complex plane is a circle, which means the first thing to do is probably to mark off a circle of unit radius, and then try to figure out when this contour touches the circumference of the circle, that is mod of L equal to 1, what angle, how far from that -10 point I am. Now, when we have circles and we are trying to measure distances, it's always better to measure angles rather than an absolute linear distance. So that's why we engineers tend to try to figure out what is this theta, where I am cutting the unit circle. Okay. So this, by the way, is called unit circle, which I'm sure all of you know. So we are trying to figure out what is this theta. Now, clearly, if theta is 0, what does that signify? It is touching -10 at least, right? We know that theta equal to 0 will essentially mean that something like this is happening. I don't know anything about what's happening before and after, but one thing for sure, if theta equal to 0 means that I'm crossing that -10, which means it's unstable, right? And theta equal to negative will mean, right? Theta equal to negative means I have encircled, right? Theta equal to negative means this is the theta, right? This becomes the theta, which means I've encircled. So theta, the count of the theta starts in this direction. That is positive theta, which means negative theta means going the other side, which means theta equal to negative means you have landed up into instability. And it also gives you a measure of how much instability, how much away from that unstable point that you are deciding. Okay, so that is why this is often a very this is a go-to margin for most circuit designers, and this margin we call it as phase margin, right? So this is a phase margin, which is the amount of extra phase at omega u loop at mod L equal to 1, that makes the system, the closed loop system, that is V naught over Vi, unstable. Okay. Yes.
System is unstable only when loop gain is system.
No, not necessarily. Right? Loop gain equal to -1, system is unstable. System is also unstable if the poles go to the right half plane. Right. So the initial stuff that we did, I could only, intuition, we could only visualize L equal to -1 is the point of instability. Right. But that is not also sufficient. If you do brute force mathematics and if you see the Nyquist derivation, that's what you are going to see, that if, I mean, ultimately the roots of 1 plus L should lie on the left half plane. If the roots of 1 plus L lie on the right half plane, you are unstable. Right. So that's what Nyquist is. Right half plane of 1. I mean, if I'm trying to find out the roots of 1 plus L, which means I'm trying to find out the roots of 1 plus L here. Correct? So the roots of 1 plus L go to the right half plane, which means what? Which means, so why, by the way, why is roots of on the right half plane is cause for instability? Because let's say there is one root in the right half plane, and we say that V naught by Vi is something times 1 by 1 minus S by P, where P is positive in this case. So let's say root is on the right half plane. So what will this mean? This will essentially mean that what will be the unit step of this, or what will be the impulse response of this guy? It will be what? Rising, exponentially rising. Eh? What is the inverse Laplace of 1 by 1 minus S by P? E power pt, right? E power pt, right? So if P is negative, then it will eventually go to 0. If P is positive, this guy will go off, right? So essentially, if you have a system and you give a impulse, you expect the output to whatever. If you have some disturbance, you expect the output to eventually go to 0, right? Because you haven't essentially, you have disturbed the system and you don't want the system to go off in a completely different direction, right? So if you give an impulse and you see that this guy has gone on to infinity, which means your system is unstable. What does that mean? This means that if the system is unstable, something like this is there in the transfer function, which means the pole is on the right half plane. Right? So pole lying on the j omega axis will give you that L equal to -1. But pole going to the right half plane will not give you L equal to -1. Right? For example, if I say L is equal to, let's say somewhere I say L equal to -2. Right? I give you that. I observe the entire L of S plane and I pick a point and say that I know that L equal to -2 is a point in that L plane. Can you tell me whether it is unstable or stable? I cannot tell. In principle, I cannot tell whether it is unstable or stable because I need to see the entire contour. Because it's quite possible that L equal to -2 means what? Let's say this is L plane. L equal to -2, what is the point? It's somewhere over here, right? This is the -1, 0 point. L equal to -2 is this point, right? So if I know that this point exists, I know that L of S cuts that point. I need not necessarily know whether it's stable or unstable because it can as well be it has gone like this, come back like this, and gone like this. It's not encircling the -1, 0 point, right? So I can always, I mean, this can still happen. So L of -2 is, or a specific value of L, you will not give you that information, whether it's stable or unstable. You have to look at the entire plot. And what am I looking for? I'm looking for encirclement. Why am I looking for encirclement? Because if it's encircled, then I know that V0, a root of the V0 over Vi, or the pole of the V0 over Vi lies on the right hand. So now we have graduated from finding that -1, 0 point only to seeing whether root exists on the entire right hand, anywhere in the right hand. Okay. Okay. So now the good thing about all pole systems are, the good thing about all pole systems are phase always decreases. Phase never increases, right? In order to have a phase which is increasing, you need to have zeros, right? So if you have all pole systems, phase always decreases, which means if it goes this way, if it goes this way, it cannot come back this way. Right? So phase monotonically decreases, which means if in case of an all pole systems, if you know that it's -2 or then it's unconditionally unstable. But anyhow, I mean, that is not for today. We'll not bother about that. So the key thing that we are trying to focus on, I hope I answered your question, or I hope it didn't confuse you further. Okay.
Also,
Yes.
when the pole is at -1,
Right.
when the passing 39, then in that case, then we not the VA graph because the pole is alone there.
Yes.
So that is all that's marginally unstable.
Right.
When you go to -1 is unstable.
That is also, the terminology is marginally unstable. Right. So that's the terminology. I mean, you can consider it to be unstable. Forget about marginal, either unstable or stable. That is also unstable. Okay. Okay. So now, I mean, okay, since he talked about this point, so let's say let's say I know that L equal to, let's say I cross the -1, 0 point, right? So let's say I cross the -1, 0 point. Not, I mean, I cut the -1, 0 point. Let's say I'm cutting this. Exactly. So the graph cuts the -1, 0 point and goes through, pierces it. Then what can you comment on the frequency at which it crosses -1, 0 point? What does that? It's not necessarily -1, 0 point, but at what can you comment on the frequency? So what is omega at mod L equal to 1? Yeah, it's omega U loop. Excellent, right? So this omega is equal to omega U loop. So omega U loop again is the unity gain frequency of the loop of critical importance. Okay. So now we know that at omega equal to omega U loop, L is equal to -1, which means what? Which means V0 over Vi is equal to infinite at omega U loop. Right? So if L equal to -1, okay, at omega U loop. So which means that if I plot V0 over Vi, note that I'm not plotting L of S, I'm plotting V0 over Vi with respect to omega. What should I see? Somewhere around omega U loop, it should start to peak and it will go to infinity. And it will probably do something like this. So this is that case of infinite gain at certain frequency. Right? I mean, we talked about these infinite gains many times before, right? When we are discussing about Y parameters, then sometime later also. So this is what I wanted to mean at that time, that infinite gain means instability. Okay, so this essentially means that you are going to have a sinusoidal oscillations at frequency of omega U loop, because this is a transfer function of an oscillator. You have infinite gain at some frequency. Okay, so again, and these are, I mean, not something, I mean, not, this is out of context, but still better to know. Fine. So now, since we know all these things right now, so now let's look at the phases of Bode plot, phases and the magnitude of the Bode plot, and try to infer, because ultimately we'll be drawing Bode plots. So let's say we have this Bode plot, second order system. We have some P1. We have some P2, and this does this. And I know, let's say omega U loop is here. Now, I hope all of you are comfortable finding out wherever the omega U loop is given a transfer function. We have done it multiple times. So now what we need to do, we need to find out the phase. So let's plot the phase. So it will do something like this. Eventually go to -pi. And what are we looking for now? We are looking for equivalent of mod of L equal to 1. Angle at mod of L equal to 1. Right? So we are looking for so what is the angle at omega U loop? Why? Why are we looking for that? Because ultimately I know in the Nyquist, I'm looking for where the plot cuts the unit circle, right? So this is mod of L equal to 1. I'm looking for where am I cutting the unit circle, which means I'm looking for the phase at which I'm cutting the unit circle. So if I, from the Bode plot, it's trivial to find out omega u loop. All I need to do is to mark off that point in the phase domain where I am cutting the, which aligns with omega u loop, essentially the phase at omega u loop, right? So the phase at omega u loop is this. So this is 0. So this is the phase at omega u loop. Let's say this is theta, whatever it is. This is minus tan inverse, or rather, I'll just simply say angle at omega u loop. Right? So how much margin do I have now from instability? So what is theta? Theta is this. So how much margin do I have? What am I looking for? Pi, right? I am looking for how much excess phase lag I need to give to hit minus pi, right? So if minus pi is somewhere over here, so this is the margin that I have, right? So essentially, the margin that I have is in terms of 180 degree minus theta, right? The way I have drawn it, but ultimately you have to take care of negative signs and all. But so essentially, let's say theta is equal to, in a second order system, theta is equal to minus tan inverse omega u loop by P1 minus tan inverse omega u loop by P2, right? So these are all negative. So what is the margin? What is the phase margin? Phase margin will be minus pi minus of this, right? So rather this minus of minus pi, right? So basically phase margin will be theta minus of minus pi, because margin has to be positive, because I'm trying to figure out how far are we. So essentially it is pi minus tan inverse omega u loop by P1 minus tan inverse omega u loop by P2. In case of a second order system, you can do the maths and figure out how much is the phase margin. Okay. Any questions till now? Okay. So now let me tie it back to the critically damped case, right? In case of a critically damped case, what was the condition for critically damped for zeta equal to 1? What was the condition? Omega u loop has to be 4 times P2, right? Sorry, P2 had to be 4 times omega u loop. So firstly, we had to ensure that P1 and P2 are far apart, right? We have to ensure that P2 is 4 times A0 times P1. And also we have to ensure P2 is equal to 4 times omega u loop. I mean, both of these two are corollary of each other. You want to ensure one, the other gets ensured, but still it's better to write. So if that is the case, how much is the phase margin? Pi minus. So what can you comment on this first term? Omega loop by P1. This is omega, that ratio is very high, very small. Very high, right? So, so if that is very high, what can I comment on tan inverse of that? Minus pi by, yeah, so this is 90. Minus tan inverse, whatever is this, omega loop over P2 is what? 1 over 4. So this comes out to be approximately 76 degree. Right? If you do the math, this 75 point something, right? So approximately 76 degree. So a phase margin of 76 degree corresponds to what? I mean, where in that? So phase margin of 76 degree means this angle is 76, which means I am probably I'm cutting the j omega axis somewhere here. right? So this will be 14 degree. Okay, so essentially your expected Nyquist for a critically damped system should look like this. Okay. So now if this is the case, so I have P1, I have P2. Where is, we already know from our previous class that where is the location of omega U loop? It is before P2 or after P2? Before P2. Omega U loop is P2 over 4. Omega U loop is P2 over 4, right? So essentially omega loop will be somewhere here. So for a good system, it should look like something like this. And the phase contribution due to P1, since P1 is far below omega U loop, doesn't appear to be the way I have sketched, but it will essentially become minus 90 degree at omega U loop. And this P2 will give you an additional 14 degree before it goes off to minus pi. So essentially, this guy will be 76 degree. That is your margin. Okay. Okay. Fine. So another conclusion, another hack, because we tend to oversimplify things as circuit designers, and all designers tend to do that. So another oversimplification of this is to say that to see at omega U loop, at the UGP, is the system, what is the slope of the system in this case around omega U loop? Slope of L of S? Minus 20 dB, right? Minus 20 dB per decade. And this is essential because if it's not minus 20 dB per decade, what does it mean? It means P2 is before omega U loop. Right? If P2 is before omega U loop, what will be the slope at omega U loop? Minus 40. Okay. So if P2 is before omega U loop, your phase margin will be better or worse than 76 degree? It will be worse because of what? This guy is anyway giving you minus pi by 2. This guy will give you more than 45 degree because P2 is before omega U. P2 is before omega U loop. You have tan inverse of minus 1 and higher, right? Tan inverse of something which is more than 1, which means you will get more than 45 degree, which means your additional phase lag. This guy is only giving you 14 degree phase lag. You will get an additional phase lag of more than 45 degree, which means it's worse than critically damped, right? It will be under damped. So that is not particularly good. So the hack that circuit designers use often to understand if a system is usable or not is to find out the slope of the Bode plot around omega U loop. If the slope of the Bode plot around omega U loop is minus 20 dB per decade or looks like a first order system, in most probably it is also stable, right? So see, we have this stability is a huge branch of mathematics. Right? It comes from complex algebra, it comes from complex analysis, complex calculus, lot of theorems broken down into one statement. Does your system look like a first order system around UGB? Again, lot of assumptions, not always true, but the systems that we generally tend to use, which tend to have open loop real poles, if you adhere to these assumptions, this entire gamut of stability analysis which have been developed through centuries can be emphasized into one statement. Does your system look like a first order system around omega U, around UGB? Or does your system, if the slope of the system equivalent to minus 20 dB per decade around UGB? If that is true, your phase margin will be better, right? At least more than 45 degree. So in that case, your system is stable. Okay, make sense? Right. So now, what circuit designers did was we said that we'll generalize this. we know all this critically damped and all these things are only for second order systems. Zeta valid for only second order systems. But we know that, again, we also know that we cannot have only second order systems. Our systems actually have third order, fourth order, fifth order, I don't know how many poles. So then how do I analyze, how do I draw an analogy between the things that we already know and the things that are beyond mathematics, like beyond any analytical calculations, right? So what we essentially said that we will calculate phase margin for any system, any order system. And if that phase margin is equal to 76 degree, we'll consider it to be critically damped. Right? To take a third order system, fourth order system, phase margins are easy to calculate because Bode plots are easy to do. L of S you can always plot, find out the angles, right? So once you do that, all you have to look for is one data point, right? It's like a headline data point, right? You don't have to go through the entire article. Just look at the headline of the news and say that, okay, what is that point? What is the phase margin? If that is 76 degree, it's critically damped, right? That's what we are going to say. But you have to be careful. That's not strictly true. Critically damped thing is only true for second order systems, but we are trying to get an analogy because ultimately we will iterate, right? Once we develop a system, we put it in a simulator or we put it in a breadboard and we'll iterate, but we need to at least know what to iterate for, right? So this is what we are going to iterate for. We are going to see what is the location of the additional poles with respect to omega U loop. If the location of the additional poles with respect to omega U loop, if the additional phase for those additional poles is only 14 degree, then I know it's like a critically damped system and we are good. Okay. So again, what I'm essentially saying is, let's say your L of S is a third order system where it is 1 plus S by P1, 1 plus S by P2, 1 plus S by P3. And we want the system to be not only stable, but stable enough, that is, it doesn't ring and all. So what we are looking for, we are looking for a phase margin of 76 degree. So what do I know? So what is the method now? The method will be plot L of S. Fine. So P1 will mark off P1, P2, P3. I will mark off and we'll see. Let's say I observe this. And I find out the angles. So now walk me through what am I going to see? This size, let's say I put it in the simulator or I did a hand calculation and I found this plot. So now I want to see whether this actually adheres to what phase margin. What should I see? Oh, sorry. Correct. Yeah. Thank you. So go like this, right? So, so now if I have to find out the phase margin, then what should I see? Find out omega U loop. So the way I have sketched omega U loop is here. So now what is the next thing that I need to see? The angle at omega U loop, right? So let's say I see the angle at omega U loop. In this case, what will be the angle at omega loop? Minus tan inverse omega U loop by P1 minus tan inverse omega U loop by P2 minus tan inverse omega U loop by P3. So this guy clearly is giving me minus pi by 2. And in this case, the way I have drawn, what can you comment on this guy? Is it more than 45, less than 45? More, right? Because the ratio is more than 1, right? So it will give you more than 45. And I will get an additional due to this also. So clearly it's not critically damped. Okay, so if it has to be critically damped, then P2 has to be above omega loop, which means probably my idea, wherever should I probably should have omega u loop somewhere here. Right? So this should have been the new omega u loop. If this is the omega u loop, then probably my margin would have been good. Okay. So by the way, this is minus 270 now, because third order system, it can go to all the way to minus 270. Okay. So again, the key thing to note is one pole will definitely be at a very low frequency, because we saw that, right? Pole splitting is required. One pole has to be much lower than omega u loop, which means that pole is essentially giving you minus pi by 2. Whatever is the additional poles, the phase contribution of the additional poles are less, right? For critically damped system, it's only 14 degree, right? If I say the phase margin of 60 degree, which means the contribution of those additional poles will only be 30 degree. So depending upon what the system you are designing, you decide on the location of the poles. Okay. Make sense? Okay. So now let's go back to that. We started all these things, right? So let's go back to our two-stage common source amplifier. And we saw that in the previous class. What were the two poles of L of S? By the way, this is closed loop. For L of S, you have to break the loop and then find out. So what were the two poles? So P1 was, let's say P1 was associated with C1. So if I say L of S is equal to 1 by 1 plus S by P1, 1 plus S by P2. So what is P1? Yeah, right. 1 over RDC1, and P2 was 1 over RDC2. Again, because not for this system, but for this system, right? When I have broken the loop, L of S is for that system. And this is an open loop system in which we can figure out the poles by looking at the time constant associated with each capacitor, if possible. In this case, it's possible, so we could figure that. And then we said that P1 and P2 have to be far apart, and so on and so forth. And in order to split them, what did we do? We put a additional capacitor CC. Right? You remember last class? We put an additional capacitor to put P1 to a lower frequency. So now this should make sense with respect to whatever we have done till now. So P1 and P2, if C1 and C2 are of similar order, RD is the same, then P1 and P2 are close by, which means I will be having mod of L something like this. Omega u loop will be here, which is after P2, which means your system can be unstable or close to instability, right? At least not critically damped, right? So what did we do? We said that we are going to put an additional CC in parallel to C1. So the new P1 will move this side. P1 will probably be here, which means your plot should look something like this, right? So this becomes, if you move P1 sufficiently low so that omega u loop is appropriately placed with respect to P2, then you can get the phase margin, the requisite phase margin. Okay, make sense? Okay, so now so is there any other way of, this is, by the way, it's called frequency compensation, right? So we are changing the frequency plot of L of S, right, to make the system stable. We are compensating for that excess phase. So since we are compensating for the excess phase to make the closed loop system stable, this is called frequency compensation. So is there any other way of pushing the pole P1 to a lower frequency other than adding this capacitor where I have shown. You can still add capacitor, but is there any other way of moving the pole to a lower frequency? Yeah, RD you can do, but I mean, you can only do so much, right? I mean, you have seen the simulation assignment unit. It's not very intuitive to increase RD beyond the value. I'm giving a hint. You can still add capacitor, but I don't want to add it between C1 and ground, between that V1 and ground, right? Which we call this V1. You have done this before in this class, Miller, right? So I can put this capacitor between these two nodes. If I do that, what will be P1? If I do that, what will be P1 approximately? Again, G by C. G is in this case GD or 1 over RD by a capacitance. What is the equivalent capacitance? C1 plus 1 plus the gain of the second stage, which is GM. We call this GM2, GM1, GM2 times RD times CC. Okay. So this is good because in the previous case where I had put capacitor between V1 and ground, let's say I required 10 picofarad, just pulling out a number. Let's say I had the 10 picofarad capacitance. With respect to that, can you comment on the capacitor required in this configuration? Again, the question is, in the previous case, when I had put the capacitance between this node and ground, let's say the CC required happened to be 10 picofarad, right? So now I'm saying I'm not doing this. I'm doing Miller. What will be the CC, effective CC required? More than 10 or less than 10? Less than 10, because that CC seems to be amplified by the Miller effect. And if GM times RT is, let's say, 10, 20 dB, right? So then you can see that the size of the capacitor reduces by a factor of 10. Right? So the 10 times smaller capacitor acts like a 10 times larger capacitor, right? So that's good. That is definitely good. Now, but even better thing happens. And the thing that happens is, you can appreciate that by looking at this Bode plot. In this Bode plot, when I had added this extra capacitance, let's say CC here, right? So it moved P1 from wherever it was to a lower frequency, but did it do anything to P2? No, right? I was not affecting P2. But now using Miller, will it affect P2? So approximately where will P2 go? Approximately. So again, conductance by capacitance. What is the conductance approximately? So this is with Miller. What is the capacity? What is the conductance approximately? What determines the conductance? RD is 1, definitely 1 over RD will be there, but there will be something in addition to this, right? Approximately again. How do you find out the conductance? You apply a test voltage at the output node and find out the current, right? So if we apply a test voltage here, again, in the open loop sense, right? If we apply a test voltage here, one current will flow through RD, definitely. So that is this 1 over RD term. But what's going to happen? It will excite some voltage here, and that will excite the GM, and it will pull current. So what is that fraction? Right. So it will be GM2 times CC by C1 plus CC. Right. So this will be the pole, and this will be the conductance, and capacitance is C2 plus the series combination of C1 and CC, right? Right. So So can you comment on whether this pole location is at a higher frequency than P2, lower frequency than P2? Let's say CC is of the same order as C1. This is at a higher frequency because now you know that GMRD is definitely more than 1, and that in the numerator in P2 is more than 1 over RD, definitely, right? So the conductance part has increased. Capacitance has also slightly increased, but not as much. So essentially, the new P2, this guy will also move, right? So essentially, if I have to sketch it again, so let's say P1 and P2 were here without compensation. With Miller compensation, this P1 will move this side, and this P2 will move that side. Okay? So P1 will be at 1 over RD times GM2 RD times CC, and P2 will move somewhere here, which will be approximately GM2 times C by CC. So your new plot should look something like. So as you can see in this case also, can you comment where the new omega u loop will be? It will be at a higher frequency than the earlier one, or the lower frequency for the same phase margin. With respect to the plot on the top, between these two, where I compensated you in the bottom, I compensated using Miller. This is with Miller. This is without Miller. So between these two, can you comment where, for the same phase margin, where will I connect the omega u loop? Whether omega u loop will be at a higher frequency or the lower frequency? It will be a higher frequency because now P2 has shifted to higher frequency. That I can afford to move omega u loop to a higher frequency, right? Because since P2 has moved to higher frequency, the excess phase is omega u loop over P2. Right? If P2 has moved to higher frequency, I can afford to move omega u loop also to a higher frequency, which essentially means ultimately, even though we want circuits to be stable, we also want circuits to be fast, right? Having a higher UGB means my amplifier will work as an amplifier till higher frequency, right? So it is beneficial if any technique gives you a stable circuit, but with a higher omega u loop, right? So hence Miller way of compensating gives you a kind of a higher bandwidth, right? So we'll discuss this in more detail in the following classes, but this is essentially to give you a primer, right? So I understand today's class might have been packed with multiple concepts, but I worked under the assumption that you have seen all these concepts in some other courses. The motive of this class was to put everything together. Okay, so I'll post assignments after in sometime next week. We can revise these concepts and get up to speed. Okay.